So we got into conditional probability a little bit yesterday because I knew I was going to be out at a conference today. And essentially what we got to was this. This notation wants the probability of A given that B is a must, essentially. So out of all of the items in B, the number of items in B will be your denominator. How many of them are also in A? So essentially, your number of items in B is your denominator in that case, and in your numerator, it's the number of items that are in really both A and B. Really, out of all the ones that are in B, how many are also in A would be how you calculate the probability for that, and then obviously vice versa for the second one. So this next example, actually for the first time, is showing us a Venn diagram with 3 categories, so owning a cat, owning a bird, owning a dog. So just to look here, this middle number would be the number of people who own all 3, a cat, a dog, and a bird. So 2 people own all 3. These 10 here is just the overlap of the cat circle with the bird circle. And then down here is your cats with your dogs. And then these 2 are the birds and the dogs. And then this is dog only, cat only, bird only. So some conditional probabilities to look at here. So the probability of owning a cat given that you own a bird. So out of all of the people who own a bird, like look at your bird circle. That's 10, 11, 12, 13, 14, 15. There's 15 bird owners. Out of them, how many are also owning a cat? So how many are also in your cat circle? That's these 2 sections. So look up at the board if you're not. These 2 sections are people who are also owning cats and own a bird. So that's 12 out of 15. Part B, the flip of that. What is your probability of owning a bird given that you own a cat? So look at your cat circle. There's 10, 20, 6 plus 2, 28. So out of those 28 cat owners, how many of those 28 also own a bird? 12. So the order definitely matters. Okay, 12 out of 15. If you're a bird owner already, there's an 80% chance that you'll also own a cat. On the other hand, if you're a cat owner already, 12 out of 20, then there's only a 0.43% chance that you'll also own a bird. Which means really there's just lots of cat owners that own just a cat. Obviously 16 of them don't also own a bird. But for whatever reason, if you already own a bird, you're much more likely to have a cat. On C, probability of owning a dog given that you own a bird. So out of all the bird owners, 10, 12, 14, 15 of them, how many also own a dog? Just these 4, 2 and 2. And on the flip of that, what's the probability of owning a bird given that you own a dog already? So out of all your dog owners, 15, 17, 19 dog owners, how many of those also own a bird? 4. Lastly, out of all your dog owners, so C given D, out of all your dog owners, we've got 19 of those. How many of those dog owners also own a cat? These 8 right here. And out of all your cat owners, what's the probability of owning a dog? So where's my cat owners? We've got 28. Out of all of those, what's the probability that they also own a dog? 8. So there is an example of A, a Venn diagram with 3 circles, and B, practicing more of that conditional probability. So a survey was taken to examine the relationship between hair color and eye color. The chart below shows the proportion of the people surveyed who fell into each category. If a person was picked at random, find each of the following conditional probabilities. Show the calculation you used. Find the probability that the person picked had brown eyes given that they had blonde hair. So, out of all of our blondies, go to your blonde. Out of all of these, 0.35. How many of these also had brown eyes? 0.10. find the probability the person had red hair given they had green eyes. So, out of all the green-eyed people, given that they had to have had green eyes, so you're looking at your green-eyed row, which is a total of 0.25. So, out of that 0.25, how many of those had red hair? 0.15. So if you calculate these individually, this is a 29% chance. So if you have blonde hair, there's a 29% chance you also have brown eyes. If you have green eyes, there's a 60% chance that you also have red hair. That's very interesting. That's like, the Irish stereotype, red hair, green eyes, which is interesting. If you have the green eyes, they're saying you're way, way, way more likely to have red hair. 60% chance. Part C is this idea of dependence or independence, which is really a key word on your Regents that's come up on every single test so far. Are these events independent? And the two events that we're going to look at on our first example of this is, does having red hair, seem to have some dependence on having green eyes, or vice versa? Meaning, is there something about having green eyes that made us more likely to have red hair? And even though you might think this is telling, we really don't know anything yet. Here's how you have to decide whether or not two events are independent of each other or might have some sort of dependence or causality between them, something causing the other thing. You want to look at your probability of having red hair on its own. If you're just a regular person, what's your probability of having red hair? And if you look up here, it's 0.20. So if you're just a regular person, the chances of you having red hair are 20%. But now look at the probability that you would have red hair given that you have green eyes, which we did in the example above already. It's 0.60. So the difference in this, they're both the probability of having red hair, okay? This one's just for any old person, the probability of having red hair. This is if you have green eyes, and we know that you have green eyes, now what's your probability of red hair? And obviously it skyrocketed. It went from a 20% chance for an average person to a 60% chance if you have green eyes. So if there's a jump between the two of these, that indicates that somehow this second feature made you more or less likely somehow, or could have made you more or less likely to have red hair. There's obviously the chance that it's coincidence, just based on the people surveyed, but this is such a big jump, we would say that this is probably due to some cause, although the Regents is very particular. We are not allowed to say that two things are dependent because we cannot tell if it was a coincidence, but rather we say they're clearly not independent. So these are not independent events. The only way they would be totally independent would be if the probability of having red hair stayed the same whether or not you had green eyes. And that's defined down below. They're independent if the probability of B is exactly equal to the probability of B given A. So the probability of event B happening didn't change at all based on whether or not A happened. They were the same no matter what. If that's the case, they're independent. These were not the same. So these are not independent. There is likely some sort of strong correlation surrounding having green eyes versus red hair. And this just says the order doesn't really matter. We can do the probability of A and compare that to the probability of A given B. These are both calculating the probability of A, and if they're exactly the same, that means whether or not B happened had no effect on the probability of A, which stayed the same regardless. So I just copied that down on the back because that's something we're going to want to look at. And this very first exercise asks us to really essentially fill out and complete a table, which shouldn't be terrible. So the female category looks like the most obvious one. These need to add up to 92. So far, 46 plus 12 plus 17 only adds up to 75. So take 92 minus that, and there should be 17 females in that category, which also makes the car column make sense. The total for bike riders is supposed to add up to 69. We already have 17 females, so 69 minus 17 females is 52 males. Can do the same thing in our bus category, 27 total on the buses. 12 of them are females, so if I subtract that 12, I get 15 males. And then my 129 in my male column, of my 129 males, 52 and 15 and 28 are already accounted for, leaving 34 walkers. And then we can grab our total here. Walkers, 34 plus 46 is 80. And then our grand total, whether you add vertically or horizontally, should be the same. 221 if I add horizontally, and you just might want to double check that 80 plus 45 plus 27 plus 69 is also 221, which it is. And then we will use this table to answer the following probability questions to check for independence or not. Did the probability of W change? And here, did the probability of F change? So on the probability of W, that's walking, probability that someone walks, there are 80 walkers out of 221 people. Which is 0.36. So there's a 36% chance you'd be a walker. Now, what is the chance that you're going to be a walker given that you're a female? So in other words, we're about to find out if being a female made people more or less likely to be a walker. Or maybe it didn't affect it at all. Maybe it will still be 36% chance you're a walker, regardless of being a female, in which case they would be independent. So out of all of our females, we got to solely look at the female category because we're given that we're a female. So out of those 92, how many are walkers? 46. So we're about to find out 46 divided by 92 is 0.50. So your chance of being a walker increased when you were a female. So we would say these are not independent, meaning, we don't need to elaborate on paper, but for you guys it means that something about being a female did correlate with being more likely to be a walker. And this just switches the order around. So we see at the top it can be in either order. Compare the probability of B with the probability of B given A. Or you can do the probability of A compared to the probability of A given B. So we're just flipping the order and looking at the probability of female versus probability of female given W. What's most important is whatever's first in the given probability part needs to be the one that you calculate on its own. So in this case, probability of female needs to be compared with probability of female alone. So if you look at your number of females, excuse me, 92 out of the total 221, that is 0.42. And then your probability of being a female, given that you're a walker, you want to look just at your walker category, which is 80 kids. Out of those walkers, how many are female? 46. So 46 out of 80 on my calculator gives me 0.58. So you should see the same result, not the same numbers, but the fact that they're not equal to each other. So something about the probability of being a female was 42%. If you were a walker, and we knew you were a walker, our chances of grabbing a female from that crew was much higher. So something about becoming a walker made us more likely to be a female, so not independent here as well. So at this point, you should be getting a worksheet for homework that you may work on for the rest of the class.